Okay, thanks very much. So I'm going to talk a little bit about galaxy formation in general, and also in this new flavor of smooth particle hydrodynamics that we call SPHS. And so one thing I would like to do, one thing that we'd all like to do, is to try and get from some initial conditions, say the cosmic microwave background radiation, via some simulation, some n-body code, to evolve those through to the present day. And by comparing these with observations, we can hope to try and constrain both galaxy formation and cosmology. So this is the basic schema. This is what we would like to be able to do. And of course, in order to be able to do that, we need to have robust, reliable cosmological simulations that model all of the important physical forces. And so I'm going to try and give a sort of a summary of a sense of where I think we are and which bits of those calculations are robust and which bits are going to require more effort on our parts. So the first and most important force is, of course, good old gravity. And the idea here is that we solve Newton's laws on the background of an expanding Friedmann-Robertson-Walker metric. This is the collisionless n-body method, which is now very mature, and there are lots of experts in the audience. Here's a simulation from Doug Potter from the University of Zurich. This is showing you the collapse of a structure that's going to come together and form a galaxy of about the mass of the Milky Way. Yellow is high density, blue is low density. And in this particular simulation that models only the collisionless dark matter fluid, we've assumed that dark matter is cold. That means it can collapse on pretty much any scale down to the resolution limit. And it's collisionless, which means it doesn't dissipate. So the structures that form are roughly round. Now, as I said, these simulations are quite mature and well understood. Here's another example from Volker Springel. This is the Aquarius simulation. And I want to draw your attention to these four massive subhalos. As you go from 18 million particles to 4 billion particles, you can really see this remarkable convergence between the results. And so I think that at least for cold dark matter, things are looking pretty good. But as we heard from Tom Abel and Oliver Hahn earlier this week, for warm dark matter, the situation is perhaps less rosy. This is a lovely plot from Wang and White, 2007. This is the cumulative mass function of halos in a warm dark matter cosmology. And this is for different simulation resolution, so 64 cube particles all the way up to 512 cubed. And you see this characteristic upturn in the mass function. And all of this, these little halos are disappearing as we raise the resolution. So they're spurious numerical structures. And the particular worry is that not only does this converge incredibly slowly with CPU cost, it may not even converge on the right answer. That's not clear. But you see that even this purple line is different, really almost all the way back to the green line when you look in detail. And when we start talking about doing 1% accurate cosmology with Euclid and so on, these things may be an issue, and not just for warm dark matter simulations, but perhaps also for cold. So one of the things I've been doing, and this is led by Alex Hobbs, who's here, is trying to understand the origin of this problem and see if we can do something about it. So one idea we had is that, well, maybe it's just force softening. So this is my very silly schematic diagram of how an n-body simulation proceeds. We put down these particles that really we should call superparticles. They represent large regions of the flow. And they have some grid initially, which is distorted, with some sort of mean spacing that I'm calling delta x. And so what you don't want is that these two particles physically interact like two massive bodies, because they're supposed to represent large regions of the collisionless fluid. So the usual trick is to employ a force softening. And if you were going to guess what the force softening ought to be, you might guess that it should be at least of order 1 or 2 interparticle spacings in order to suppress this two-body interaction. But then immediately we have a problem, because the universe collapses, and if it collapses to something smaller, then the interparticle separation shrinks, and if we have a fixed physical force softening, then this will now be really large and will have terrible spatial resolution. So the usual solution to this is to maintain a fixed force softening, but shrink the force softening so that at the end of the calculation we can resolve the things we're interested in. But that means, of course, at the beginning of the calculation it's too small. And this means that at the start we can pick up spurious two-body effects. And what will spurious two-body effects do? There'll be an attraction, there'll be scattering, maybe there'll be spurious small halos. So our first idea was, let's adapt the force softening with the density dynamically, and maybe this will solve the problem. So here it is. This is a simulation of warm dark matter filament with adaptive force softening, and unfortunately still lots of spurious halos. And you can spot these spurious halos quite nicely because they're regularly spaced with the initial grid spacing. So this didn't help at all, and in fact actually it makes it worse if you adapt the force softening and try to maintain energy conservation using these Dan price correction terms. So what's going on? Well, we think what's going on is exactly what Tom alluded to earlier, which is that gravitational collapse is not isotropic. So in fact, for any, you can think of an ellipsoid, it has a short axis and it will collapse first along that short axis. And so if I do that, the density goes up, and if I adapt the softening just on the density, then my softening will shrink. And so we end up with this scenario where really I should have one softening in this direction, a different softening in that direction, but my adapting on density will pick the smaller of the two, leading to discreteness noise in the y direction. So as a very crude and simple way to deal with this, we could simply say, well, let's not adapt exactly on density, but have a novel form of adaptation that picks the larger of the two softenings in this scenario. And you can think of this as being sort of the opposite of what Tom's doing. He's trying to capture a more accurate force when the flow becomes anisotropic. We're deliberately doing a less accurate force. So there's no free lunch, but this is a very simple algorithm that can be put inside a tree code. So if you do this, and you run the warm dark matter filament again, then things look very promising. The spurious halos are gone. We now form just one single lump inside that filament. And this is really hot off the press. This is still work in progress, but we do hope to have the paper out this year. We're still looking at convergence and how the mass functions change and so on. So watch this space. OK, so if we think we understand how to model gravity, of course, the whole universe has lots of gas in it. The gas collapses to form stars and galaxies, the thing that we're all here interested in studying today. And at least within galaxies, the gas can be reasonably approximated by the inviscid Euler equations. So we now want to add those in to our calculations. And there are two main tools on the market. The first are called Eulerian techniques. And so we can imagine that you have a lump of gas here, and you solve finite difference equations on an Eulerian grid. And if you want, you can also adapt that grid into regions of interest. And these techniques are very mature, at least in the non-adaptive case, dating all the way back to the 50s, if not earlier. They're well understood, and they certainly do solve the fluid equations well. If they didn't, planes would fall out of the sky. But there are other techniques available to us, and they do have certain advantages. And these are Lagrangian techniques. And the idea here is that you throw down particles on top of the fluid to represent the fluid itself, and these co-move with the fluid, rather like this. And one example of such a Lagrangian technique, or the most popular and well used, is smooth particle hydrodynamics. And this has a whole bunch of rather nice features, that it's a Galilean invariant, so it's geometry-free, Lagrangian. And I think this is really the big one, because when it comes to analyzing the simulations, you can really track back where individual parcels of gas came from. That really helps us understand what happened in these complicated simulations. It couples to a particularly fast gravity solver, this FMN solver, which can go as order n, as shown by Walter Danon. And so all of these nice features are very good. And the final one I want to draw your attention to is that we're now trying to solve sufficiently difficult problems where we don't know the answer, that we really want to have more than one technique. Especially we want to have different techniques with different kinds of error. And then when these agree, we build confidence. But, as we heard already from James, there's a problem. At least the classic or canonical, what we might now call old-fashioned SPH, doesn't do very well for problems where you have fluid mixing. James already showed you this now infamous blob test from Oscar Agertz. Here is the grid code. The blob nicely breaks up. Here is SPH looking like the jellyfish. And so when I saw this in 2007, I immediately wanted to try and understand what's going on and whether we can, if we understand it, whether we can solve this problem. So what you want to do if you want to understand what's going on here is simplify the problem to a nice problem where you know the answer. So imagine that I zoom in here on the surface of this blob, and you can think of this as just being a shearing flow. This is a dense fluid, less dense fluid, and these are moving past one another like this. And to make it a controlled experiment, we can put a sinusoidal velocity across the boundary, and this should excite an instability called the Kelvin-Helmholtz instability. And this instability is extremely well understood. It's not only understood analytically in the linear regime, it also can be done with experiment in the laboratory. This is a real experiment of fresh water and dense salt water, and you get this lovely characteristic Chandrasekhar roll. So this is the right answer, and we know on what timescale this happens as well. The question is, what happens when you do this with classic SPH? You see that after one Kelvin-Helmholtz time, there's a distinct lack of a Kelvin-Helmholtz roll. And the reason for this is twofold. The first thing is force accuracy. Now what I've done here is I've picked the usual cubic spline kernel. People normally run with 32 neighbors. And I've beefed this up to 128 neighbors because you can prove that if you raise this neighbor number, you ought to improve the force accuracy, although at the cost of some spatial resolution. But what's happened is that all the particles have clumped together into these hard spheres, and you can see visibly the gaps between all the particles. And this occurs because if you do a linearized stability analysis of the equations of motion, you can prove that they're unstable to clumping for this choice of kernel with this many neighbors. But the good news is you can then derive kernels that are stable for large neighbor number. Here's an example, and immediately you start to do better. You see the onset of a nice Chandrasekhar roll, and this is just because we've improved the force accuracy. Go to a higher order kernel again, and we do a little bit better. But as James alluded to, this is not the whole story, right? Improving the force accuracy is one piece in the puzzle, but if we now evolve this Kelvin-Helmholtz instability for 3 Kelvin-Helmholtz times, we get a nice roll, nice-ish 2 rolls, and we end up with a lava lamp. And so this is saying that basically, as James showed, we're not getting mixing on the level of individual particles. It's still being suppressed. And so what's going on here? Well, the way I like to think about this is a problem for any Lagrangian method. So imagine I have 2 particles, and they have fluid properties, here the entropy, mass, and velocity. And we have some equation of state, here a polytropic one, P is A, rho to the gamma. And now imagine these 2 particles approach each other at some point P. Well, as they get close to each other, they smooth their density. That's what smooth particle hydrodynamics means. So they agree on their density at this point, but they carry with them their entropies. So at point P, they have discretely different entropy, but the same pressure density. And this means that there'll be a pressure discontinuity. And indeed, this is exactly what you see in classic SPH, this large pressure discontinuity at these points of convergent flow. And a large pressure discontinuity drives a force, because the force is the gradient in the pressure. So this creates an artificial surface tension, which is extra to the tension that James was talking about, that causes a repulsion between the 2 different fluid phases. And so this is clearly bad. And so the question is, what can we do about it? And I would argue that essentially the solution to this problem is very similar to the concept of artificial viscosity in SPH in the first place. We already turn on artificial viscosity at point P because we don't want the momenta, mv1, mv2, to be multi-valued. And so in fact, we don't want any fluid quantity to be multi-valued. Multi-valued fluid quantities are not a valid solution of the Euler equations. So the idea is that we should try to detect when this is happening, this scenario, and turn on some numerical dissipation. And this is not an attempt to model physical or unresolved dissipation. This is simply turning on dissipation to ensure single-valued fluid quantities. We want enough dissipation that there are no multi-valued quantities, and then ideally we don't want any more than that, so we don't introduce unnecessary error. So this dissipation is a numerical error. What I'm arguing is that it's a better kind of numerical error than doing nothing, because if you do nothing, you get the pressure discontinuity, and this drives pressure waves that travel through your fluid and spoil convergence. Okay, so if you craft some switch, we use a second order accurate switch, and you do this and you improve the force accuracy, then we can return now to the Kelvin-Helmholtz instability problem. This is with a density contrast of 1 to 8, and we can set the thing running, and indeed we now get the correct growth time. We see the characteristic Chandrasekhar rolls, and then the system goes into the nonlinear regime. And so this is all very encouraging. And I should say that we're, of course, not the only group doing this. This is the particular methodology we use. But in fact, I think almost everybody using SPH now does something along the lines I've just described. Maybe not exactly the same, maybe not quite as accurate, but something in that direction to improve SPH. And so I think really we're getting to the stage now where SPH can be taken seriously again as a solution of the Euler equations and as a real tool for doing astrophysics. So I'd now like to talk about how it makes a difference, in fact, why we go to the trouble of having a really good hydrosolver, what happens, what changes. So here is this Santa Barbara test that James also spoke about. This is a high resolution modern reworking of this done by Chris Power. Here it is in classic SPH. This is the gas density, and this is a non-radiative galaxy cluster. So there's no cooling, it's just the equations of hydrodynamics and gravity. We allow this cosmological cluster to come together, and we ask what are the gas properties at the end. And if we go from classic SPH to SPHS, immediately you can see the difference. Lots of little halos suddenly gone. And this is the sign of the effect that you would expect. You can see it here for this halo. You can see the gas stream coming off. This is happening because we're now capturing this round pressure stripping process more faithfully. And this means that small halos moving into this cluster have their gas taken away before they can arrive at the center. So what this does is has a rather dramatic effect on the entropy profile as a function of r. This is in units of the virial radius. Here's the SPH number. This is for increasing resolution. So as you go up and up in resolution in SPH, this entropy profile converges ever more on an ever shallower entropy in the center. This is the SPHS result. This is from Ramsey's, which shows really, I think, remarkable agreement. And one thing I want to draw your attention to is I've not tuned the dissipation to try and get the same result as Ramsey's. I have actually no freedom there. This is showing the amplitude of the dissipation in SPHS. And because that turns on just before the shock and it turns on just after, off just after the shock, it's rather insensitive to the amplitude. And so if I have no dissipation, so 0, like classic SPH, then I get a line that's something like the SPH line. But the minute I have this dissipation switch working, then independent of the magnitude, I get the nice converged entropy core. And so I see this more as a verification of the result from the AMR code rather than an attempt to reproduce it. And you see that here also now in the redshift evolution. This is showing you the central entropy profile, density, temperature. This is the SPH result. Here is SPHS in blue. And these green triangles are from Ramsey's. And I find this agreement really quite remarkable. No tuning here. This is just what comes out from the calculation. This shows us something else quite interesting. That at early times, the classic SPH result's very noisy. And then at around about redshift 0.4, though, you see this real departure, right? This is where the SPH code starts to move towards an ever lower central entropy while the other codes stay high. And what's happening here is this is around about where the mergers stop, or most of the major mergers stop. And so all of the low entropy particles left lying around here at this point in SPH sink down to the center of the cluster potential, whereas in SPHS and Ramsey's they mix in the IGM. Okay, so in the very last part of the talk, hopefully I've convinced you that we understand, or we are well on our way to understanding how to do gravity. I think we understand how to do non-radiative hydrodynamics, but this is not going to form galaxies. We need to add more physics, and the next piece of physics to add is cooling, radiative cooling, allow the gas to condense, form stars. And the minute we switch this on, we open Pandora's box, and things get nasty. And immediately there's a problem, because now gas can become genes unstable, and this genes instability is hierarchical. So you can have genes instability all the way down to the resolution limit. So our resolution then sets a new scale in the problem. So if this is the particle mass, here it's 1 million solar masses per particle, so particularly bad resolution. Then you can imagine some minimum genes mass. And here I've just said for the sake of argument, so let's say it's about 100 times the particle mass. It doesn't really matter what this number is, but some number of particles is going to define a minimum genes mass that I can actually correctly resolve. And then on a phase diagram, this is log temperature, log density. These lines of the genes mass basically appears as these lines along here. And essentially anything below this line, if this is my particle mass, I can't properly resolve. So anything below this line is genes unstable, but I don't have enough particles to resolve it properly. And so the question is, what do we do? And I think this has not really been answered. It's one of the things I'm hoping we can get at with Agora. Should you just not worry about this? Or should you attempt to prevent anything in the simulation from living down here where it can artificially fragment? And so our strategy is to switch on a polytropic equation of state along this line, and so to forbid collapse below what we believe is our resolution limit. As we raise the resolution, the line moves, and then at some point, you can then check for numerical convergence by stopping evolving this line. And then as you raise the resolution, you're getting finer resolution in your shocks, in your resolved gas, and so on. But you're not getting further and further collapse. Thank you. And so I stopped here deliberately. This is 10 to the 4 solar masses per particle. That's about the resolution of Eris. And that then gives you exactly what you want for a cooling floor of about 1,000 K and star formation at 100 atoms per cubic centimeter. But the depressing thing, if you like, from this plot is if you really want to get down to a 10 K cooling floor with a star formation threshold of 100 atoms per cubic centimeter, then you are going to need an extremely small particle mass. And this point is not often made. So I think some of the claims of resolution that we hear are perhaps not as good as claimed. Okay, so Alex is going to tell you a lot more about this. So this is more of a teaser. But obviously now we have cooling, we have star formation. In these simulations, we've done a very naive feedback. We simply return heat to the surrounding gas. And what I'm showing you here is 2 simulations of just a cooling halo. So I set up a hot halo gas in hydrostatic equilibrium, and then we allow it to cool and condense and form stars. On the left, you have classic SPH, and on the right, SPHS. And they really are now like day and night. And hopefully Alex will convince you the reason for this is that there's a numerical instability that sets in the halo here and drives the formation of all of these cold blobs. And it's particularly dramatic in this simulation because the cold blobs actually form stars and then go supernovae, and so the whole thing completely diverges. In SPHS, this instability is gone. And so, as I say, Alex will tell you much more in the next talk about all of the different implications we've found so far for galaxy formation in SPHS. I just want to make one more point before I put up my conclusions, and this is that when you try to converge in these simulations, you have to be quite careful. So this is exactly the simulation I just showed at some late time after the initial starburst, and the hot halo gas is just sitting there doing absolutely nothing. And you can double the resolution here, and it will still sit there and do nothing. You can lower the resolution by a factor of 10, and it will still sit there and do nothing, and so you might believe that you're numerically converged. But look what happens if I just go up a factor of 5 in resolution. Suddenly I can resolve a new scale in the problem, which is the length scale of these cold filaments, and suddenly I start to see this cold gas streaming down into the middle and fueling further star formation. If I go up another factor of 5, these filaments start to collapse and condense and form stars. So the difference is less dramatic, but there's still another stepwise change. And so when we do these kind of convergence studies, we have to be careful. We need to move up factors of 5 or 8 or more in particle mass to convince ourselves we've captured all the physics. And there's no substitute for thinking about what the key scales in your problem actually are. So that's where I put up my conclusions. Thank you very much.
So, questions?
No more cold blobs.
Mm-hmm.
There are cold blobs in the Milky Way. There are high velocity clouds. So are you worried that SPHS might be overmixing?
Well, I mean, it might be overmixed. I'm not too worried. I mean, actually, as I showed you in the last slide, we do have cold blobs forming in those filaments, right? But also remember that these are very toy simulations with very idealized initial conditions. So there are no cosmological blobs. There's no cosmological infalling gas. And we haven't hit the converged resolution yet, even that I showed in the plot. So I think that there's still a lot of work to be done. I mean, I'm convinced.
My point is we shouldn't use no more cold blobs as an objective our simulation, because then we are not going to be able to
I don't know what's going on with our Milky Way, but at the same time we know.
Well, but we see, you make a map in H1 of the Milky Way.
No, but that's a different
and it doesn't look like a smooth.
I'm not claiming that every blob you see in SPH is wrong. There is a numerical thermal instability one should worry about, but I think if you're using gasoline 2, which has dissipation, or our code, then you don't have to worry about that anymore. Yeah.
Plus he had cold blobs formed in the end, right? It's just that it wasn't just randomly, they were forming in filaments.
Yeah.
Where's Alexander? Next speaker, please come in.
Okay.
We continue. But did you run it like a test? We could run simple tests. There is a gas which should be thermally unstable. Do you produce thermal stability?
Yeah, right? that I think would be nice.
Because it's you modify one term, another term, and you cure some problem, but at the same time it might show up something else, like Sedov solution, thermal instability.
With some finite perturbation.
Yeah.
It's not numerical.
Yeah.
But see if you clock.
So, yeah, exactly.
This is a good idea, yeah. I mean, we've shown we don't get an instability where you shouldn't, but we haven't shown you do where you should.
That's right.
Yeah.
So.